Welcome to this training session on lithium-ion battery manufacturing. In this course, we will walk through the complete journey of how lithium-ion batteries are made, from the very beginning of raw material preparation, all the way to the final assembly and quality testing. Our goal is to help you understand each step of the process, so you can connect your daily work in the factory to the bigger picture of battery production. Let's begin our journey from the front to the end of Li-ion battery manufacturing.
Now we move into the first main stage of battery production, electrode manufacturing. This is the foundation of the entire process. It's where we take raw materials and turn them into the electrodes that store and release energy inside the battery. In this section, we'll walk through each step of electrode production, mixing, coating, drying, pressing, and cutting, so you can see how the quality of electrodes directly affects the performance and safety of the final battery. Electrode manufacturing is the foundation of battery making, and it includes 5 key processes. First is mixing. Here, anode and cathode powders are dissolved with binders and solvents to create a wet slurry. This step is crucial for ensuring that materials are evenly blended. Second is coating. The slurry is spread onto thin metal foils, copper for the anode and aluminum for the cathode. The coated foils are then dried, allowing the solvent to evaporate. Third is calendering, or compressing. The coated foils are pressed flat to achieve a uniform thickness. This step directly affects the amount of energy the electrode can store and the consistency of the battery's performance. Fourth is slitting. The wide coated foils are cut into narrow strips so they can be used in individual cells. Finally, the electrodes are integrated, meaning they are prepared and aligned for the next stage of cell assembly. The quality of the battery depends heavily on these steps. Any mistake in mixing, coating, or pressing will carry through to the final product. Electrode manufacturing, process equipment. These 2 diagrams illustrate the process of making electrodes using various types of equipment. On the left, you see the 5 main steps of electrode fabrication, each with its own machine. We start with the vacuum planetary mixer for slurry mixing. Then, the slurry is coated onto foils using an automatic coater. Next, the foil is pressed through a roller calender for uniform thickness. After that, a slitting machine cuts the electrode into strips. Finally, the electrode making machine prepares the pieces for assembly. On the right, you see an integrated system that combines coating, drying, and calendering into one continuous line. The foil moves through tension rolls, coating applicators, a drying system, and calender rolls without stopping. This integration saves time, improves accuracy, and reduces handling. These machines are the backbone of electrode production. When they run smoothly, we achieve consistent, high-quality electrodes, which in turn lead to strong, reliable batteries. Now let's look at the actual machines used for electrode manufacturing. We begin with mixing, done in a vacuum planetary mixer. This equipment combines the anode and cathode powders with a binder and solvent to form a wet slurry. A good mix ensures the right consistency for coating. Next is the automatic continuous coater. It spreads the slurry onto copper foil for anodes or aluminum foil for cathodes, and then dries it to allow the solvent to evaporate. The goal here is an even defect-free layer. After coating, the foils pass through the roller calender. This machine compresses the electrodes to the target thickness and porosity, improving energy density and uniformity. Then we move to the slitting machine, which cuts the wide electrode rolls into narrow strips that match the size of the cells. Clean edges are important here to prevent short circuits. Finally, the electrode making machine integrates and prepares the finished electrodes for the next step, cell assembly. Each of these machines must run precisely. When they do, we get stable, high-quality electrodes, which are the backbone of a reliable battery. Electrode manufacturing, mixing, electrode slurry. The electrode manufacturing process always begins with mixing. Here, the active materials are blended into a uniform slurry. The process starts with the dry mixing of powders. For the anode, that's usually graphite with conductive carbon black. For the cathode, it's lithium metal oxide powders. In both cases, binders and conductive additives are also included to hold everything together and improve electrical conductivity. Next comes wet mixing. where the powders are dispersed in a solvent inside large mixers, such as the vacuum planetary mixers shown in the picture. This turns the powders into a smooth, homogeneous slurry. The second picture shows what this looks like once coated. Here, a roll of copper foil with black anode slurry applied. The third diagram breaks down the ingredients into the active material, the conductive agents, and the binder that holds everything together, keeping everything stable. This step may look straightforward, but it is actually one of the most critical processes in cell manufacturing. Parameters like viscosity, density, solid content, and even air quality and humidity must be carefully controlled. Mistakes here carry forward and can affect more than 30% of the final battery quality. Mixing is relatively low cost compared to other steps. However, it is time-consuming and often limits the overall production speed. That's why consistency, monitoring, and discipline in this step are essential for the whole line. The next step after mixing is coating and drying. In this process, the slurry is spread evenly onto copper foil for the anode or aluminum foil for the cathode. Slot die coaters, like the one shown here, apply the slurry through a narrow gap, ensuring a uniform and precise layer. Coating machines in modern factories are massive. At CATL, for example, slurry is coated onto copper foil that's 6 micrometers thick and runs nearly 4 kilometers long, moving at speeds of about 80 meters per minute. As the foil passes through the line, it is dried immediately, and the solvent is recovered. The foil must be coated on both sides, which can be achieved by rewinding the roll, using a tandem coater, or a simultaneous two-sided system, as shown in the diagrams. The key here is consistency. Every micron of coating thickness matters. If the layer is uneven or if dust particles become trapped, the battery may exhibit poor performance or discharge too quickly. That's why these machines are fully automated, continuous, and enclosed so the process stays stable and contamination-free. Electrode manufacturing, drying plus coating, oven and solvent recovery. After the slurry is coated onto the foil, the next step is drying, which is carried out inside long industrial ovens, sometimes as long as 70 meters. The foil passes through multiple heating chambers, typically set at temperatures ranging from 80 to 160 degrees Celsius, as shown here. Drying is not just about removing solvent. 3 things happen at the same time. 1. The solvent evaporates, carried away by hot air or sometimes infrared heating. 2. The polymer binder spreads evenly across the electrode film. 3. The active material particles settle into place. As drying continues, the coating layer shrinks and its internal structure develops. Ultimately, the solvent vapors, such as NMP, which can be toxic, are captured and sent to a recovery system, rather than being released into the air. The result is a clean, stable electrode layer, ready for pressing in the next step. The precision of this drying stage is critical. If it's uneven, the electrode can develop cracks, poor adhesion, or weak spots that affect battery safety and performance. Electrode manufacturing, drying plus coating, slot die technology. Here we see the precision coating tools used in electrode production. The first picture shows a slot die head, which is today's leading technology for battery coating. In this method, the slurry, sometimes called ink, is pushed through a narrow slot across the foil. This ensures a very uniform layer, with thickness controlled down to just a few microns. Slot die coating can make layers from as thin as 10 nanometers to over 100 micrometers, depending on the process. The second diagram compares different coating methods. The Dr. Blade and comma bar techniques are older, simpler approaches, but they don't always provide the same precision. Slot die, by contrast, is highly controlled and consistent, which is critical for large-scale, high-quality battery production. After coating, the solvent evaporates, leaving behind a pure film of active material on the foil. This technology is also used beyond batteries, in solar panels, advanced materials, and other energy applications. For us in the factory, the key point is that slot die coaters provide us with the accuracy and reliability needed to produce stable, safe, and efficient batteries. Electrode manufacturing, coating, process monitoring and control. This diagram illustrates the coating process from start to finish. We begin on the left with the foil roll being unwound. The first step is to apply the top coat of slurry onto the foil. Immediately after coating, the foil passes through a dryer to remove solvent and stabilize the layer. Next, the foil is flipped, and the bottom coat is applied, followed by another drying step. By the end of the line, both sides of the foil are evenly coated and dried, ready for calendaring. What makes this system powerful is the inline inspection frames you see marked along the process. These inspection systems continuously monitor the quality of the coating, its thickness, uniformity, and surface condition, while the line is in operation. This monitoring and control are critical. It allows us to catch defects like streaks, uneven coating, or pinholes immediately, instead of discovering them later. That way, we reduce waste and maintain efficient production. So, in simple terms, foil in, coat dry one side, coat dry the other, all while inspection systems keep watch to ensure the electrodes meet strict quality standards. Electrode manufacturing, calendaring. Once the electrode film leaves the dryer, it retains a high porosity of approximately 60%. To improve energy density, the electrodes are compressed in a process called calendaring. In calendaring, the electrode passes between two heavy rollers under high line load pressure. This reduces the thickness of the active layer and lowers porosity to approximately 30 to 35%. The result is a denser electrode that can store more energy per unit volume. Calendaring also improves the adhesion between the electrode coating and the current collector foil, making the film stronger and less likely to peel or crack during later processes. The graph below illustrates the effect of line load on coating density. As roller pressure increases, both cathode and anode density rise until they reach a maximum limit. The balance is important. Too little pressure and the electrode stays weak, too much and it can lose flexibility or crack. In short, calendaring is about finding the right pressure to produce electrodes that are dense, durable, and energy efficient. Electrode manufacturing, slitting. After calendaring, the wide-coated foil is too large to go directly into a cell. The next step is slitting, cutting the foil lengthwise into narrow strips that match the exact cell design. The machine here shows how this works in practice. The coated foil unwinds, passes through precision slitting blades, and comes out as multiple narrower rolls. Each roll will later be stacked or wound into battery cells. Quality in this step depends on 3 key checks. 1. Electrode width. It must meet the design spec within microns. 2. Edge flatness. The edges need to be smooth, not wavy. 3. Burrs. Any tiny metal burrs left from cutting can cause short circuits later. That's why slitting machines are tightly controlled, often with the aid of laser or camera inspection. So, while this step appears to be a simple cutting process, it's actually a precision operation. Good slitting ensures safety, consistency, and high cell yield down the line. Electrode manufacturing, electrode finalizing. We now proceed to the final step of electrode manufacturing. Finalizing the electrode with tabs. Tabs are small metal connectors welded to the current collector foils of the anode and cathode. Their job is simple but critical. They carry electrical current between the inside of the battery and the outside power source. The finalizing process includes several sub-processes. 1. Electrode ear cutting, preparing the spot where the tab will be welded. 2. Laser cleaning, removing any contamination to ensure a strong bond. 3. Tab welding, attaching the tab to the foil, usually by laser, ultrasonic, or spot welding, depending on the cell format. Quality checks here are vital. We inspect the welds visually, test the tab peel strength to ensure they don't detach under stress, and measure electrical resistance to ensure the current flows efficiently. On the left, you can see a pouch cell structure where the tab is welded to the foils. On the right, the diagram illustrates the optimal welding methods for each cell type: cylindrical, pouch, and prismatic. Once tabs are attached and verified, the electrodes are complete and ready to enter the cell assembly line. This concludes step 1 of the electrode manufacturing section. Thank you.